Now this is one thing. Yeah. So one thing is the number of these square roots of -1 increases exponentially. So the number of my sort of square roots of -1 permutation operators increases exponentially with n. And again, just to remind you, that's sort of how the Hilbert space goes in terms of the dimension of Hilbert space with the number of qubits. What I want to do is in some sense, think of these sequences as both, like in the symbol space, state space duality, think of them as both representing the state of a system at an instant in time in state space, and also in the symbol using that phi homeomorphism, think of them as also representing a sequence of time, a time sequence with respect to some partition, some binary partition of this underlying attractor which the nonlinear dynamics is given. Now, between total unsynchronization, between lack of correlation between pairs of sequence and complete synchronization, you can obviously get partial synchronization. And indeed, in nonlinear dynamics, it isn't just total or unsynchronized states. You can get states of partial, you can get dynamical systems which are partially synchronized. So in particular, one can think of two sequences, let's call the first one S1 and the second one SI, such that the synchronization, the degree of synchronization lies somewhere between 0 and 1. And one could think of a sort of one-dimensional array of these oscillators, which, where the degree of synchronization sort of, as it were, decays away in this cosine or sinusoidal state. So in other words, we can start to build in wave-type dynamics. So let's consider our sequence S, say here. Minus S is where things are perfectly anti-correlated. So every 0 symbol goes for a 1 symbol. So the correlation is -1. If I choose any one of my 2 to the n minus 1 square roots of -1, then this produces a symbol sequence which has no correlation. It's orthogonal to S. I can do that there. And then minus one of those square roots of -1 gives me something which is uncorrelated with this guy. Sorry, is anti-correlated with this guy and uncorrelated with either of these two. And more generally, one can define sequences where, as I say, the correlation is varying by cosine phi, where phi is some phase angle. This is technically how one would define S of phi in terms of symbol sequences, but I won't dwell on that. The thing is, you can end up writing a kind of two-sphere where a point on the equator is some sequence of zeros and ones, equal numbers of zeros and ones. As you go along the equator, each point has a symbol sequence, but the correlation with S is decreasing until you get to here where the correlation is 0. And this is the square root of -1 operator acting on S. And as you go round back to the antipodal point, then you get to minus S, where the correlation has gone to -1. Or you can go up in this direction, where the sequences, again, start to decorrelate from S, but where you go towards just a sequence with nothing but zeros, or in this direction, nothing but ones. And again, this will be uncorrelated, this sequences will be uncorrelated with this one, which has an equal numbers of zeros and ones. And in particular, if you get to stop at this point here at colatitude theta, then by construction the number of zeros will be equal to cosine squared theta upon 2. So when theta is 0, it's all zeros, and when theta is pi by 2, it's a mixture of zeros and ones. So this is a bit like the block sphere for a qubit in quantum theory. So this is the block sphere for a sort of standard Hilbert space description. So my picture then is to try to think of the wave function as, in some sense, not in the kind of usual way of some sort of superposition, which is hard to know what it means, but actually as this symbol sequence. So, and thinking again about the symbol sequence as a kind of duality between a set of possible outcomes, a time sequence of outcomes, or a state. I am thinking now of going away from this sort of somewhat indeterminate sense of the state vector in quantum theory to something rather definite. A definite state with a definite value given by that by the symbol sequence, but which, if one thought of it as in terms of a time sequence of perhaps measurements, it would give you a completely random set of zeros and ones. And this guy here would be another definite symbol sequence where this I, in a sense, now becomes one of my 2 to the n minus 1 square roots of minus 1, and is uncorrelated. It has an uncorrelated symbol sequence with the symbol sequence here. And there is a kind of a parallel with the Born rule in quantum theory, which is that if I were to define a norm on my symbol sequence as in this form, then when A is 0, this is 0, and AI is 1, this is 1. So this is basically giving me the, if you like, the probability that if I chose if I randomly chose an element in my symbol sequence, would it be a 0 or a 1? So by defining this norm on the symbol sequence, I can interpret this norm as giving me the probability that any one of the elements AI is equal to 0. Or in other words, it gives me the frequency of occurrence of, say, the 0 symbol over the 1 symbol. So in other words, the norm of that would be cosine squared theta equal to 2. So I have, with these symbol sequences and with these representations of square root of minus 1 as permutation operators, I have something which, in some sense, seems to encode wave dynamics. And if you remember, I talked about this linearity of F, the shift map having some, even though the underlying state space dynamics was non-linear, there was some linearity in the shift sequence allowing me to define a kind of addition. So I have something which seems to me starts to get something like wave-particle duality. The particles being the individual symbols, in some sense, and the waves being these square roots of minus 1 representations plus this linearity of the shift map. And it sort of reminds me in a vague philosophical way about the pilot wave, the Bohm sort of stuff, that one really is talking about both at the same time, not one or the other. The duality of the symbol sequence versus state vector approach. You know, they're both there at the same time. That's just a philosophical remark. So, this is really the kind of the main point here. So when we come to kind of think about, if you like, tensor products and so on in quantum theory, I guess the corresponding thing in my own picture would be of where the state vector is a kind of set of these symbol sequences, and if the system is entangled, it merely means there is some correlation between the symbols. So from a kinematic perspective, entanglement in this picture would just be a kind of denoting some correlation, partial correlation or complete correlation between symbols. And incidentally, these correlations are invariant under permutation transformation, so I could